So we are having 3 talks this afternoon, so it's going to be a long afternoon. So Andy is going to be the first one, and he's going to talk about the varieties of reversal. So Andy, the floor is yours.
Thank you. All right, thank you everyone for coming. And, I'm going to talk about some things that Peter Philip would call philosophical mumbo jumbo, and hopefully that'll go okay. So I wanted to say some things about reverse mathematics from a philosophical point of view, as it were. And I thought that one thing I wanted to start with as a kind of prelude was an old discussion about what foundations are, because sometimes people wonder to what extent is reverse mathematics driven by interest in foundations, whatever that's supposed to be. And that term foundations is contested. So in this old dialogue, gosh, it's almost 30 years now, on the Foundations of Mathematics mailing list, Dave Marker and Steve Simpson and a bunch of other people argued about this for the first out of 1,000 times. And so Marker says this thing that, look, foundations is any work that sheds light on mathematical practice, mathematical thinking. And then he gives an example. To me, one of the most important points in the foundations of mathematics is the duality between algebra and geometry. Well, the fact that the Zargesian projective planes can be coordinatized by division rings is arguably just a theorem of geometry. I think it is an important foundational result because it clarifies this duality. Well, okay, so that was what Marker said. And then Simpson responded, no. He said, this is too broad. Most high-level mathematics has this quality of shedding light on broad areas of mathematics. That doesn't make it foundations. What I mean by foundations is the Frege-Russell-Hilbert-Gödel line, formalization of mathematical practice and the study of properties and limitations of such formal systems. So one of the things I want to do today is reconcile these two views, because I think in reverse mathematics, that's something that happens. And just to make that really explicit, I wanted to start by looking at reversals that happen in geometry. You'll hear much more about this in the next talk from Victor Pambuchian, who will speak about reverse geometry. So as he points out here, and you'll be hearing more about it in an hour or so, the kind of thing in mathematics where we look for the axioms needed to prove a theorem goes way back. So this is something that the ancients were doing. There's reason to think that the reason Euclid gives the proof of the Pythagorean theorem that he does is because he knows that if he didn't use the parallel postulate, he couldn't get the theorem to be true. So there's some sense that he had a reversal in mind. This becomes explicit by the time of the guy Pappus. So there's a whole school of geometrical work where they're looking for reversals. Now, this also continues, and I'm not going to dwell too much on history here, but just another fact that in the Middle Ages, so one of my colleagues here in Paris, Vincenzo De Risi, has done work on medieval mathematics in Europe, and not even just medieval, but even in the early modern period, so in the 16th, 17th century. That one thing you find when you look at textbooks is mathematicians proving the axioms, which sounds very strange. Aren't they axioms? Doesn't mean we don't prove them? But these mathematicians are proving the axioms. They're trying to find the definitions that will suffice for proving the axioms. And here the axioms just mean the ones you know from Euclid. So this is a big task in these books, for instance, by Clavius, which is the translation of Euclid that's known to Descartes, for instance. So this is something that goes on. They're proving the axioms all the time, and the books therefore look pretty weird to us now, but that's just what was going on. So another example that's the one that Dave Marker was talking about is the Zarg's theorem, which maybe you know the statement of it. If not, I'll just sketch it for you. So the theorem says that if you have two triangles, here we're looking at the planar version, so they're in the same plane, and they're such that the lines that connect their corresponding vertices intersect at a point, then de Zarg's theorem says that the corresponding sides are going to have lines. They're going to intersect. Normally we're thinking of this in the projective setting, but that doesn't really matter much of the time, but it will matter to us a little bit here. So de Zarg's theorem says that the 3 points of intersection of the corresponding sides in this case are collinear. So this is de Zarg's theorem, and it was of a lot of interest to lots of mathematicians, but in particular, Hilbert got excited about it in his Foundations of Geometry because he was able to show that the Zarg's theorem is in fact the necessary and sufficient condition for a plane to be embeddable in space. So this is a kind of reversal as I want to explain. So it had been long known that you could prove de Zarg's theorem in spatial geometry. That was known already in the 17th century by Zarg himself. So you look at the spatial version where you've got triangles that are possibly in different planes, and you can project that down into the plane itself and prove Zarg's theorem that way. So this is known by lots of people. But then in the 19th century, people start to wonder, is that necessary? Could we avoid using space to prove this plane theorem? And Felix Klein says no, but he doesn't really have a proof. Then Hermann Wiener, in a lecture that Hilbert attends, because it's the reason that Hilbert gets excited in Foundations of Geometry, hears this lecture. Wiener also says no, but doesn't really have a proof. Peano then gives a proof, but it seems like nobody reads it. And finally, then Hilbert gives a proof that people then read and understand. A proof, that is, that you must use space to prove planar Zarg's theorem, at least if you're allowing yourself only projective methods. If you let yourself use coordinates or metric methods, then you don't have to. And so I just wanted to observe that this is a reversal over the axioms of projective geometry. Zarg's theorem is equivalent to the embeddability of a plane in space. So it has consequences for thinking about the curvature of space. And so that's a kind of a reversal. And the way that Hilbert proves that is also maybe familiar to you because it involves these results about division rings that, again, Marker was talking about. So Hilbert had known, lots of people had known that you could prove Zarg's theorem using coordinates, the same kind of boring proof that you would have learned in analytic geometry, as long as the coordinates came from a division ring, or if you were being a little bit more slack in a field, you wanted to use commutativity. But Hilbert was able to show that if you have the axioms of a division ring, those are actually provable if you just start with a plane in which you have Zarg. So you can recover the coordinates even if you don't have them to begin with, and those coordinates will have the right algebraic structure. And he also does the same thing for fields, but you have to assume a geometric theorem a little stronger called Pappas' theorem, which I'm not going to go through. So these are examples, again, that I think we ought to count as reverse mathematics or even reverse geometry, which, as I said, Victor will say more about. But also the people who were doing this thought of it this way. So this guy Wiener I mentioned in this lecture that was so inspiring to Hilbert at the German Mathematical Society meeting in 1890, 1891, Wiener writes this thing where he says, and this is going to echo the language you see among the reverse mathematicians today and all of the textbooks today. Wiener says, one can ask of the proof of a mathematical theorem that it use only those assumptions on which the theorem actually depends. The minimal imaginable assumptions are the existence of certain objects and certain operations through which said objects are connected to themselves, among themselves. If it is possible to string them together so that theorems are generated, then one obtains of these theorems a self-sustaining domain of science. So this is the kind of talk that you find in all the textbooks now that we all take as boilerplate in reverse mathematics. We're looking to find something like minimal assumptions of existence axioms. Here the existence axioms aren't set theoretic, but rather geometric. But the framework, I want to say, is the same. And Hilbert buys into the same thing. So Hilbert is giving lectures already in the beginning of the 1900s where he says, this is what axiomatics is. We're trying to not just to discover new theorems, but rather the position of a theorem within the truth that we know and their logical connections in a way that indicates clearly which conditions are necessary and sufficient for the grounding of that truth. So again, the kind of language that we're so familiar with in reverse mathematics. And that makes sense because as Walt has shown in his paper with Walter Dean, with Sean Walsh, Hilbert's work later that becomes the kind of recursion theory, computability theory that now is so much a part of reverse mathematics, originates in the work that Hilbert does with Bernays later on. So there's a direct bridge between Hilbert's interests in these more geometrical sides of reversals to what we think of now. That's not the story that I'm going to tell, but it's a story that in part has already been told, and there's more to say about it. So now I just wanted to hit some of what you might think of the boilerplate, just to show you both the echoes of the past, but also to point out some things that are lurking in the alleged boilerplate. So here is as you all know, Richard Shor's article from 2010 on reverse mathematics is the playground of logic, where he says, look, this is what you're doing in reverse math. You're trying to calibrate the strength of mathematical theorems in terms of the axioms typically of set existence. This was started by Harvey Friedman, and his goals were both philosophical and foundational. what existence assumptions are really needed to develop classical mathematics, and what other axioms and methods suffice to carry out standard constructions and proofs. So here you see the word philosophical and foundational, those words are coming into play. And if you care to think about the thing I said about Dave Marker and what foundations are, you might even think here foundational doesn't just have to mean trying to figure out what it's connected with predicativism or finitism or whatever. You might think, well, just anything that's telling us the location of mathematical theorems with respect to each other, how things hang together, is in fact foundations of mathematics as well. And that's a line I want to take today, and I'll say more about it. Now, the way Simpson puts it in the big book is that we have this main question: which set existence axioms are needed to prove the theorems of ordinary non-set theoretic mathematics? And this is what he says reverse mathematics is all about. And here the word needed, of course, needs to be clarified. And he says that means that the set existence axioms are to be as weak as possible. So the ideal here of doing reverse mathematics in this way is to try to find weak axioms where weakness is to be understood in some antecedent way that happens to line up with foundational programs that were already popular, things like finitism and predicativism, things that Walt and Benedict and Steve already talked about. But there's another way of looking at what's going on in reverse mathematics that I think gets conflated. And a part of maybe my only goal is just to explain to you today that they oughtn't to be conflated. And maybe, in fact, I'll consider this talk a success if you tell me, oh yeah, that was obvious already at the end, because you'll just confirm that what I was saying was right. So here I think you see a different view. This is again in Richard Shor's paper on the playground of logic, where he tells the story that Dennis Hirschfeld will later on say, I couldn't do any better than tell you an example of why mathematicians are interested in reverse mathematics. This is one of those stories. So he's in Israel working on a problem with the combinatorists. The combinatorists recognizes that in their proofs, they're using methods that are beyond those of classical combinatorics. And this mathematician is upset by this, or at least wonders, is this really necessary? Usually, he says he uses compactness, but in this case, he had to use choice, transfinite recursion. So this mathematician was concerned, not that the problem was hard in the sense of combinatorially intricate and complex, after all, that was his bread and butter, but that its solution required construction procedures that seemed outside the usual bounds of the subject. His question was if there was a way to prove that no argument by compactness would suffice, and that the methods he used were actually necessary. And Richard's response is, yes, this is what we do in reverse mathematics. So notice already that this is different than looking for the weakest axioms. And as I said, that's my only point today. I'm going to go on and on, give you philosophical mumbo jumbo, but that is the main point. This is not looking for methods that are outside the usual bounds of the subject and seeing whether those are necessary. It's not necessarily the same thing as finding the weakest axioms. And I hope that I can, if that's not obvious, I hope I will convince you of that, because as I said, I'm going to try to drive that into the ground. So you see, I think, I'm going to call this a kind of, if I'm being positive, which I should be, I'm always told, there's a duality in reverse mathematics. If I were being a little bit more critical, I might say there's a kind of ambivalence. And if I were being a jerk, I would say there's a confusion. I think positive spin is always the best one. And when I say confusion, that sounds really harsh. It's not one that prevents people from getting work done, but rather maybe we don't think as clearly about what we're trying to do with what we're doing as we could. So I want to, that's, and philosophers can occasionally be good for helping them with that. That's what I'm trying to do here. So here I think this is a passage from Dennis's book that lays out a lot of the things you might be looking to do within reverse mathematics. So he says, look, you could accomplish a lot of things. You could, for instance, reveal the combinatorial core of a theorem. For example, it can tell us when a method is not just useful in proving a theorem, but in fact necessary. But in other cases, it can suggest different ways to prove a theorem or clarify the relationships between variations of a theorem. There are also foundational issues it can address by pinpointing exactly how much of the abstract machinery of set theory is necessary to prove a given theorem, or a collection of basic theorems in a given area of mathematics. So to my eyes, this is putting together a lot of different things in these quite compact 2 sentences. There's a lot of different stuff that's it's not being mixed together. It's being gone through very quickly and not differentiated from each other. And it's simply true that these are all things that you're doing in reverse mathematics. But for my money, it's good sometimes because I don't get paid to prove theorems. I get paid to think about proving theorems, I guess. Slow down and think about how these are different from one another. In part, if you're really a bread and butter mathematician and you just want to hear what's the cash value, maybe you could write your grants even more successfully to some funding agency if you could explain a little bit more clearly the different things you can accomplish with your reverse mathematics. So that's where I'm at so far. We're seeing, I think some things are getting tangled up here. I'm trying to untangle them for you. In a very recent book, so I just got my copy last week, so a book came out from 2 of the organizers of this conference in French, so by Benoît Monin and Ludovic Paté. Their book is called Calculabilité in French. So far, it's only available in French, but my understanding is that you're looking for an English translation at the moment as well. So here, they also have a very lovely section. The big part of the book is on reverse mathematics and long introduction to reverse mathematics and why it matters. So here is just a little part of it that I wanted to bring up because I think it again shows us the reflections we're trying to put on reversal. So they say reverse mathematics is a set of tools coming from proof theory and computability theory for analyzing the computational content of mathematical theorems. It permits responses to metamathematical questions such as, what are the optimal axioms for proving ordinary theorems? And what sense to give to the implication of one theorem by another? Yeah, that last sentence is a little awkward in English, so this is just my quick translation. But in French, it reads much better, I think. But the idea is that we're doing, for instance, 2 kinds of things in reverse mathematics. The one, I think, is more or less the same kind of thing that you saw already in Simpson, for instance. We're trying to optimize the methods that we're using. We're trying to find the weakest methods that we can. At least that's one way of reading optimal here. And they go on to say a lot more about what optimal means. And this is more or less what they're talking about. The second, which would be a whole other talk, I think is also super interesting to talk about how reverse mathematics helps us make sense of what implications mean. They make the observation that in reverse mathematics, you find equivalences between theorems. But isn't that kind of funny, since mathematical theorems are all true? So aren't every true statement equivalent to each other logically? So that can't be what we mean here by equivalent. So instead, we've got this notion of a base theory, and also of a very elementary logic that allows us to understand what these equivalences are really showing. So they introduced the notion of an elementary proof, and as a way that what we're really looking for, what we're really finding, is not so much semantic, but rather a kind of syntactic observation that when we have an implication in a reversal, by equivalence, we have a case where what we know is that one theorem is provable in an elementary way from another theorem. And that gives us some information that's beyond just all truths are equivalent to each other. There's something about the way that the equivalence works that's important. I think that's a point that, as I said, deserves a lot more reflection. I'm not going to do that for you today. I thought I would be able to, and then I thought there's just too many things to talk about. I'm already talking about too many things. So too bad for now, but fantastic section, and you should all read this book right away. So I think this is something I kind of already said, that there's this idea that optimality can be measured in a kind of computational way, or if you like, thinking of it proof theoretically in terms of interpretability strength. And Dean and Walsh argued, I think convincingly, that this emerged from ongoing work in computability theory, proof theory, and descriptive set theory. There's a history there that gets you from Hilbert and Bernays to Freeman and Simpson to today. And I think you also see obviously reflected in this notion of combinatorial core that Dennis uses, and this idea of computational content from Benoît and Ludovic. So these are notions that explain how in reverse mathematics today we're trying to measure optimality in the specifically computational context. But I think Simpson, as I said, there's this kind of duality. There's another sense in which we can think of reversals that's lying in just about all these people. It was in Shor, I think it's in what Dennis said, and it's here in Simpson also, where Simpson says there's another way to understand what the main question is asking. And this comes in section 1.9 of the book, when he quotes Harvey, who says, when the theorem is proved from the right axioms, the axioms can be proved from the theorem. So what does right mean? So you can go back and look at the original paper of Harvey, and here Harvey puts it a little bit differently. He says the questions underlying the work presented here on subsystems of second-order arithmetic are the following. What are the proper axioms to use in carrying out proofs of particular theorems or bodies of theorems in mathematics? What are those formal systems which isolate the essential properties to prove them? And when you're a philosopher and you hear the word essential, then you start to get a little bit of a twitch, because that's a dangerous word in philosophy. It's the kind of thing that we've been trying to think about for 2,000 years. Like, this is all Plato cares about, our essence, what's essential. So when I saw Harvey put it this way, I thought maybe this isn't the same thing as mere optimality. It's trying to calibrate the strength or weakness of our theorems. Maybe there's something else going on here. And one reason, so again, like I said, I'm trying to hit you over the head with this point suit. There are, at least so far, two ideas emerging. One, that reversals reveal the weakness of a statement, the optimal axioms for proving it with respect to this measure of weakness, for instance, computationally. But alternately, reversals might show us what are the right, proper, essential, appropriate, or natural axioms for proving a statement. That's other language you find. And you're going to think, some of you are going to think those are the same thing. And I really want to try to convince you that they're not necessarily the same thing. Even though in the context of contemporary reverse mathematics, they seem to be the same thing, because we're measuring essential or correctness in terms of optimality. But what I'm trying to say is you needn't do so. And in fact, it makes it all more interesting if you don't make that conflation. So I'm probably halfway through, so there's still a point to be made. One reason to think that this is a point being made is because Simpson makes this enigmatic reference to Aristotle at this point in the book. So this is just a screenshot of section 1.9, which is where he introduces reverse mathematics, and he says, we begin the section with a quote from Aristotle. Reciprocation of premises in conclusion is more frequent in mathematics because mathematics takes definitions, but never an accident for its premises. A second characteristic distinguishing mathematical reasoning from dialectical disputations. And this just comes from Aristotle's, one of his main books on logic. And then Steve says, the purpose is to introduce one of the major themes of his book, reverse mathematics. Because of course the book itself is called Subsystems of Second-Order Arithmetic. Reverse mathematics is just something you can do with those systems. And what you can do with it, apparently, somehow is related to Aristotle. So again, you probably, for the most part, the audience here doesn't think about that art, because why would you? Aristotle. Dead, really old, and it's hard to read. It's kind of boring. But, you know, again, as a philosopher, you're hit on the head with Aristotle. You think there's maybe something more to this. So I'm not going to talk a lot about Aristotle here, but I want to use it as an introduction to the thing I really do want to talk about, because it's connected. So Steve has got Aristotle totally right. I asked him over email about this once, and we had a good discussion. He's going to tell me I shouldn't take his offhand remarks about mathematics too seriously, but I do. There was a reason he quoted Aristotle. He knew what he was doing. So Aristotle does have this account on which we're trying to look for, ultimately, reversals. So what's the story? Really briefly, he says, well, look, we're trying to come to know things, and we don't think that we know things until we have grasped the why. That's to say, its cause. And then Aristotle says that in mathematics, at least, the why is ultimately referred to the what, to the definition. And what are definitions? Aristotle says definitions are that which state the essence of a thing. So this notion of definition is not the same kind of notion of definition that you're used to in mathematics, where you think of them as being stipulative. Definitions, according to Aristotle, are real definitions. They tell you what a thing is in some real sense. So, and there's of course long debates in antiquity, in the Middle Ages, and even today about what real definitions are they nonsense. Different questions. For Aristotle, they're not, and I think for Steve also, they're not. And I think also for lots and lots of mathematicians, they're not, because as an excellent philosopher of mathematics has pointed out, this task of finding the right or proper or correct or natural definition is a major research objective of mathematicians, and it has been forever. So for instance, J.B. Tappenden, he's the person who did this, argues that for Riemann and Dedekind, for instance, this was really their goal. Yeah, you could prove theorems, but getting the right definition, that was really where it was at. In the case of Dedekind, the right definition of the real numbers, and ultimately of the natural numbers. Getting those was hard work, but the idea was to get essential definition, that which stated what they really are. You might not care, but they cared. And the big question then is, why would we, how would we know we succeed? Like, that's maybe one reason not to care. It just doesn't feel like this answers to mathematical standards. We know when we have a proof, but do we know when we have the right definition? You might just say, well, I know it when I see it. But it would be better to have something more precise. And here I want to make tentatively a suggestion that reversals are something that can play a role in this regard. That this is something that Aristotle already had in mind. So again, I just put the quote that Aristotle, that Simpson gave. This is something that's remarked upon by all the scholars of Aristotle, that Aristotle thinks of proving from conclusions to premises, not premises to conclusions. So for Aristotle, everyone knows that his logic is about reversals. That this is, and the idea here is that for Aristotle, if we're looking for these real definitions, this is what explains why reversals are so important in mathematics. So there's a story here on which you could view the presence of a reversal as giving a precise answer to the question of, have we found a real definition of a mathematical thing? Now, this is just a sketch, but it's a sketch that I think deserves some attention. But that's not all. So there's something else that's been lurking in the background with remarks, for instance, of Shor and of Hirschfeld on what we're doing in reverse mathematics. And it comes right out of the same model of Aristotle looking for essences. Because Aristotle argues if you've got proofs that go from the essence, then your proofs can never prove things about a different kind of thing that you start with. So if you're talking about a geometrical object, geometrical theorem, you can't prove that by using arithmetic. To do so would cross kinds. And that's not going to be permissible if all of your steps involve essences of things. Because essences aren't mixed. Essences are of a single kind of thing. You're asking, well, what is a vector space, or what is a real number? That's a single kind of thing. It's going to have its essence, and that's what you're looking to define. In Aristotle, it follows from his logic that you can't mix areas of mathematics, or in fact of anything. Now, we saw this concern. It's not just an ancient concern. We saw it with the combinatorist of Richard Shor's example, who was arguing that, or was concerned that he was working on a problem that required construction procedures that seemed outside the usual bounds of the subject. And that was something that this person wondered about, maybe even worried about, wanted to see if there was some way to avoid that. If you could do it just by the internal methods, by the usual story, by combinatorics and compactness alone. But this is common in mathematics, it turns out. So just another example, you may know the Briançon-Skoda theorem from Algebra and Geometry. We're not going to talk about the theorem in detail. If you know it, that's great. But this is an example of a problem that's stated purely algebraically. It's about integral closures of ideals. And the mathematicians who work on this, so here's a paper from the Michigan Mathematical Journal in '81. This is not philosophers, these are not logicians, these are regular mathematicians in a kind of ordinary good mathematical journal. And they say, look, there's this proof of this theorem, that a completely algebraic statement that's based on a transcendental deep result of Skoda. And they say the absence of an algebraic proof has been for algebraists something of a scandal, perhaps even an insult, and certainly a challenge. And in this paper, they meet the challenge. They give a purely algebraic proof, and that's publishable. So the point here is that the kind of concern that Richard's combinatorist was expressing is just a normal mathematical thing to do. It isn't the only thing. Sometimes you're excited, often you're excited, when you find a proof that uses something transcendental to prove something algebraic. Maybe that's what really gets you going as a mathematician. But it isn't the only thing that gets mathematicians going. Sometimes you really want to see, can I do it in a way that stays close to what I'm up to? This was also part of the story in number theory, as you probably know. The prime number theorem says asks how many primes are there up to an integer x. We know that Legendre and Gauss hypothesized that this is going to be approximately n over log n. And finally, then, that's proved in 1896. We now call that the prime number theorem. But the proofs that we had used complex analysis from the start. And so mathematicians ask the question, a simple question like how many primes are there up to x deserves a simple answer, one that uses elementary methods rather than all of these methods of complex analysis, which seem rather far from the question at hand. And so this, again, ordinary mathematician, he's an excellent number theorist who I think is in Montreal now, in the Princeton Companion to Mathematics that Gowers put together. So this is just a simple statement about what we ought to be doing in number theory. But again, I think I want to say there's this duality, or if you like ambiguity, or if you like confusion, of the same kind that we saw in reverse mathematics between the two different things that could be going on here. Because on the one hand, he could mean that the classical analytic proof, the complex proof, is rather far from the question at hand in the sense that somehow complex analysis doesn't belong to elementary number theory, which would be a difference in kind, in this kind of Aristotelian sense. Or he could mean that complex analysis is stronger than elementary number theory, more in the sense of optimality that we saw, for instance, with the quote from Newton. So these are different again. Like I said, I just wanted to kind of continue to harp on that difference. You see it in all kinds of parts of mathematics, these two different objectives. And they both have the context of reversals, though I think I ended up having to cut out the part where I show you Takeuchi's analysis of this using PA in weaker theories of arithmetic, but we could talk about that another time. This idea was echoed by lots and lots of number theorists, that the idea that, look, the propositions of the prime number theorem relate entirely to the natural numbers. It seems reasonable that they should be provable without the intervention of such foreign ideas. Can you hear the xenophobia there? Complex analysis is foreign, and therefore should be avoided. This is totally standard language in mathematics. Sometimes. Sorry?
I've heard worse.
Yeah. So you hear sometimes direct methods within the framework of the problems themselves, rather far or not so far. That was Granville's way of putting it. These are common expressions. Hilbert had a word for this. He said that this was what you could call the aim of preserving the purity of method. That is, trying to prove theorems, if possible, using means that are suggested by the content of the theorem. And you hear, so a proof would be pure in the sense of it only uses what belongs to the content of the theorem. So other language you'll hear is extrinsic, extraneous, distant, remote, alien, or foreign. The xenophobia starts to come out at the end. There's lots of interesting things to say about the xenophobia if you want to talk about, for instance, mathematics under the Third Reich. There's a great story to be told about how they really preferred these kinds of proofs that didn't mix algebraic geometry. For instance, algebraic geometry was verboten under the regime, and you can see this in looking at the publication practices in Deutsche Mathematik, for instance. So that's another story that I'm telling. Yes, Anthony?
I mean, like Plato, for example, would complain that his contemporaries, they were using things like, and then we construct a point, he said, look, this is like, this went against this Platonic idea. Like,
yeah, sure.
You don't talk about toilets, constructions, or barf in a mathematical proof. You talk about beautiful Platonic things. Constructions were as taboo as,
but these guys publishing in the Michigan Mathematics Journal, they're not talking about Plato, right? They're just doing regular math.
No, but Plato was very adamant there.
Oh, yeah, for sure.
He would reject proofs based on no.
Yeah.
We're not carpenters building or plumbers unclogging a can. We're mathematicians. It has to be ideal.
Yeah. But when Selberg gets the Fields Medal for proving the elementary version of the prime number theorem, he's not getting a Fields Medal because the guys are appreciating Plato, right? I mean, they're just saying this is just good mathematics.
Of course.
So I'm totally with you in that this goes back for a long time. But it's one of these funny things that goes back and yet is still part of what we're doing now. And I think that what we're doing in reverse mathematics is also part of the same thing, and that it's good for us to recognize that it's not just about optimality, but it's also about sorting out the different kinds of things we're working with and knowing when we gotta use something foreign and when we don't gotta use something foreign. And recognizing that we're doing both of those things is a kind of gain in understanding. It's my modest goal for today. So I think that Granville is also not clear on this difference. I mean, I mentioned this some other time. I put some slides where I said this on my webpage at one point, and Granville read them. He wrote me this kind of annoyed email saying, "Are you really saying that I'm confused about what I'm doing?" And I had to say, that's why I decided to take a more positive spin, because he didn't like that answer. He just thought that wasn't so good. But I do think that there's two different goals that are getting mixed up there. The other goal is this one that you're familiar with from mathematics. The way Coxeter put it was just, he's talking about this proof in of a result that maybe Victor will talk about next, but doesn't really matter for it being. There's a proof of a theorem in projective geometry. This guy Kelly gives a proof using the extraneous concept of distance. Coxeter says that's like using a sledgehammer to crack an almond. We all know that kind of metaphor. That's a case where you're using methods that are simply too strong. This is why you look for optimal methods. Both of those are compatible with these readings. That's why I'm saying there's an ambivalence or a confusion, or at best, a duality in what we're doing in mathematics. This is just to say the whole talk of elementary proofs in number theory. There's a tradition of saying complex methods are not elementary. The reason for that has to do with the kind of optimality. So when I was at Illinois, I had a colleague named Harold Diamond, who's a very good analytic number theorist, and he told me that, look, it's just that elementary methods don't use analytic continuation. They don't use the Fourier inversion theorem, because these are mysterious and deep, and we don't understand them. So it's better if we could find in number theory proofs that don't use those methods. This is an optimality concern. It isn't a concern about kinds, it's a concern about strength. By the way, if anyone, I've probably asked many of you these questions before, but if anyone has done anything in the reverse mathematics of analytic number theory, I'd really like to know. I know that Kaito Yokoyama wrote his dissertation on this, worked on it during his postdoc with Steve on the reverse mathematics of analytic number theory. But I think there's a lot more to know. Just if you could make this distinction have some formal content between analytic continuation on the one hand and the so-called, just regular theorems of integration in complex analysis, if that could come out in some formal way, it would be really nice. But my understanding is that it just hasn't been much done, probably because you have to know a lot of logic and a lot of number theory to do it. But yeah, so I'd like to know more about that. So I think I'm probably getting near the end of all this time. So just like I said, there's a couple of different readings here that have been caged in terms of weakness and in terms of being of the right kind. They're not the same thing. So just a kind of quick sketch that they're not the same thing. If you have a proof of, say, a pi01 statement in arithmetic that uses an arithmetically complex set of natural numbers, or even an analytically complex set of natural numbers, they would still be only using things of the same kind. It's still just sets of natural numbers. But we would still, so in that sense, it would be objects of the same kind. But the proof would no longer be necessarily optimal with respect to strength. You'd hope that you could use something weaker. So kind is not the same as strength, and strength isn't the same thing as kind. So Selberg and Erdős, for instance, use real integration in their proof, and that doesn't seem to be part of the content of the prime number theorem. It just involves ratios and logarithms. But nevertheless, as I said, number theorists don't think that real integration is any stronger than the regular amount of complex of number theory. And that does seem to come out in the formal analysis, because the Selberg proof was able to be formalized by Kornaros and Dimitriakopoulos in TRA, I think. So these things do have, some of these results have formal analogs that are well known by now, and some of them don't. So now I said at the beginning, some of you might have the instinct that, look, if we're talking only about computational content, then these two views are going to fuse, because what's of a different kind and what's of a different strength. If all we care about is computational content, it seems to be more or less the same thing. That's exactly what computation seems to be about, how strong something is, how hard it is to carry it out. But that only is going to make sense as a part of mathematics. It won't make sense of geometry, unless you somehow think, I guess, like Brouwer, that all of mathematics is really, including geometry, it's really arithmetic down at the core. But if you don't think that, then it's important to keep this difference in mind. But it's also important because I think you're accomplishing different goals. This is a grant part I was talking about before. Because if you're looking at trying to understand the differences in kind between things, you're trying to understand how things hang together. This is what Hilbert wanted in philosophy. This is what a guy named Wilfrid Sellars wanted. He's the guy who made Pittsburgh philosophy the most interesting department in the United States of philosophy. So philosophers, mathematicians, this is one view of what we're doing. We're trying to find how things hang together. But with the second, you might be having doubts about stronger methods if you're a constructivist or finitist, and you want to know if you can get away without using those. This is what you guys were calling foundationalism before. I think foundationalism should be understood as somewhat broader, foundations in a broader sense, but never mind that for now. Right, so you might care about one of these goals more than the other. That's natural. We don't all have the same priorities. And I think this is one way in which reverse mathematics helps in the task that philosophy of mathematics is generally about, which is trying to explain, among many other things, why we reprove theorems. Something that looks to the outside to be a bizarre thing. Why did Selberg get a field for reproving the prime number theorem? Why did Bourgain get a Fields medal for reproving, for learning a little bit more about Semeretti's theorem? And I could go on and on, but we give our highest prizes sometimes to people who do something old again. And the reason is because, I think, this is a major task of the philosophy of mathematics, and the reason is that we have different goals. Different groups accomplish different goals. So I'll try to articulate some piecemeal way a couple of different goals that we see in reverse mathematics, and can then account for why we look for different kinds of proofs. So really, if this all sounds obvious to you, then I win. If it doesn't, then probably I lose. Either way, I'm done for the day. So thank you very much.
So we'll now move to questions. I see that there is a few of them. So maybe Carl first, and then we'll also have a question from Zoom.
So one thing in reverse math, especially in the second order arithmetic versions, I had the sense in some of the early writings that they were intentionally looking to cross disciplinary boundaries by being able to say, well, this theorem is equivalent to some theorem somewhere else. But at the same time, I mean, it's a very coarse, right, equivalence. It doesn't capture many things like working with a principal negation or answer some of these questions. So it's actually, in some way, it's a challenge in reverse math to answer questions. Is there an analytical proof? Is there an elementary proof? Is there a dynamical proof? Right? Absolutely. But are you looking at reverse math as trying to answer those questions also?
Yeah, I think so. Sometimes. I think so. Dennis's quote brought that out. I think that the quote from Richard Short brings that out. And that's at least one of the things that we're sometimes trying to do. Both account for mixity and accounting for non-mixity, unity and disunity.
Well, in combinatorics, I completely agree with them. Right? That you understand this core, and you measure this. I mean, in particular in combinatorics, in finer ways than with equivalences over arithmetic.
Yeah, no. I mean, one of the things I was trying to say is that maybe you find that you can't avoid mixing things together, but that's also a piece of knowledge that's good to have, right? So if ultimately we want to know how things hang together, we don't need to just assume at the outset that everything is going to fit together in this kind of pure way. Maybe what we find is things are all mixed up. So for instance, the theorem of uniformization by Poincaré and Klein is an example of a theorem itself that mixes algebraic geometry, differential geometry, a little bit of combinatorics. It's about parameterization of curves in space. This is a result that the statement itself mixes up all kinds of stuff. And so Poincaré says, look, we're looking for a pure proof of this. But purity for him means something that can mix other areas together. But ultimately, it's a question of figuring out how things hang together. And the best kind of answer to that are some kind of necessary and sufficient condition, the kind of thing that a reversal can give you. Of course, it has to be interpreted, right? Because the questions of the base theory are important here. If we're going to talk about that more, this is back to this point about elementary proofs that I think Ludwig brings up. But yeah, so I think we're both trying to defend, as it were, that sometimes areas don't get mixed, but also maybe they do. In which case, we'd like to know that is, and that tells us something about how mathematics fits together, even if the math ultimately looks pretty weird. Yeah.
Ludovic?
Yeah, well, I don't completely agree, or maybe I missed the point about the fact that reverse mathematics kind of answers the question about naturality of proof. So that I do believe there is indeed a deep link between, for example, simplicity and proof and its naturality. But at the same time, I feel like there is a very strong difference between a logically weak proof and a simple proof.
Sure.
And like often when trying to have an elementary proof, we have like a much more complicated, it turns out to be much more complicated from a human viewpoint. And also the simple fact that we are able to state statement of the kind like with Koenig's lemma is equivalent to the completeness theorem. I mean, this is something which puts like totally different areas which are foreign to each other, and so it's still able to put a link between these two. So which means that it doesn't really care about naturality, and especially in non-strict reverse mathematics, we are doing a lot of coding, and so we don't really care about like the fields or the nature of the object. We more care about like their logical strength.
I totally agree. I think that in what Diamond said, for instance, he makes this distinction that you were just talking about that an elementary proof is not simple, he says. Yes. So I totally agree with what you're saying. So I didn't mean to suggest that this is the only thing that reverse mathematics is up to, but it's good to get clear on the different things that reverse mathematics is up to. And I think your definition gave a couple of different things already. So this is productive work on figuring out what we are doing. Yeah, you're in charge, right?
Yeah, Alberto, and then I'll take the question.
Yeah, I'm actually following up on Ludovic's theme, because actually, a good example is actually the one mentioned by Shor, this Koenig duality theorem, because actually the eventual logically optimal proof in ATR naught of that theorem given by Steve Simpson actually uses an inner model to put at some stage the whole objects of your construction inside the inner model, and so you avoid using 501 comprehension by playing that trick. And that is completely external to what the statement is about graphs. It's completely, probably for Haroni, this would be even a stranger proof than his original proof in 501 comprehension, which you're using transfinite recursion or things like that, and even more than that. And just another short example, about maybe more than 10 years ago, I think, we were at a meeting in Bertinoro, maybe some of the older people were there also. And there was this combinatorialist from Maryland whose name is missing to me now, but
Versage.
Sorry?
Bill Versage. Versage, yes.
And he was saying, well, why does it happen that when we move from Ramsey theorem for pairs to Ramsey theorem for triples, I don't feel the earth shaking? That was his question. And the point is, well, because you are using the same proof for both Ramsey theorem for pairs. Sorry?
Because he was sitting down.
Okay. From the Ramsey theorem for pairs and Ramsey theorem for triples, while if you want to do a proof for Ramsey theorem for pairs which doesn't use AC naught or something, you need to work much harder, but to do a completely different proof. So from a combinatorial point of view, that's actually the nicest proof. It's just the one that goes by induction, and you can go up any linearity without any problem. So simplicity is sometimes mentioned, but I think it's far away from the typical aim of reverse mathematics, because as Ludovic mentioned, and I was just wanting to support with a couple of examples, it's actually quite completely different. The optimal proof very often is much more complicated than the original or some other proof. Still, you find a proof which uses less axioms and you appreciate it, at least as a reverse mathematician. Sometimes the proof gives also newer insights beyond the original proof. I think that's the case for the theorem Paul mentioned the other day, which I also involved. We have a completely different proof from the original one, and it's more constructive in some sense. I don't know if it's simpler or more difficult. We should, somebody read both of them and then decide. But
right, but it's how we measure simplicity here is really up for grabs, it seems.
Yeah,
right?
sure.
So sometimes, the idea here was that maybe simple means easy to understand, but what you're pointing out is that these proofs that we get via coding or other methods like that they're not at all easy to understand. But they still do accomplish the condition of getting us a result that doesn't use any hiders.
Yeah, for killing duality theorem, surely the proof in ATR is more complicated because it's the original proof carried out in a modern theoretic context. So it adds on top of the original proof more stuff of logical nature or sort of, which probably wasn't, wouldn't come to mind to Arana, which was already unhappy with using these strong plus finite definitions.
I'll just take Avi's question and I will go back to the room. Avi,
Yeah. Oh yeah.
you can either read your comment.
I'd like to be seen also.
Yeah, I'll stop sharing.
Yeah, there we are.
Go ahead, Harvey.
Sorry.
Yeah.
There. Okay, so I wrote a couple of chats. And this is a very satisfying, very interesting talk. It reminds me of something I've struggled with all the time. What is the difference between a foundationalist? I'm not sure that's the right phrase, but I'm referring to me as an example. Foundationalist and a philosopher. So if you look at the chat, I do a certain amount of philosophy until I get traction. Of course, what is traction and all that is the tricky question. So I do philosophy until I get traction. And then the traction does involve a lot of detailed, purely mathematical discoveries. Then the philosopher, then I feel like they're missed opportunities because I have this vague feeling that somehow this is not getting to everything I want to, or doesn't have enough traction or whatever. And then I do some more philosophy. Not publishable philosophy, just in the head. And then I get more traction. And then this stabilizes, and then I run, then I push what the traction was. That's what I did in connection with that's what I did in connection with RM originally, because I started the RM ideas around 1967 when I got out of school, or even before in some sense, even somewhat before, but it didn't have enough traction. And it took a while for me to actually really be able to set it up properly. So, and with the strict reverse mathematics that I'm struggling with for decades, there was a fair amount of, there was a certain amount of traction that came out of that, because that was the original conception in 2009, when when I came up with this straw man. So it's interesting, philosophically, you might be able to react to that straw man. I had set up this strong man that all of this logical strength and all of this logical investigations are totally nonsense, produced by logicians doing things talking about things that mathematicians don't do, and so forth and so on. And and this business about the inevitability of logical strength, that paper, you're probably familiar with that at least now. So, and then now I'm trying to actually set up SRM as a viable subject, which is very tricky because of the fact that if you unleash it, you wind up with a zoo of 7,000 systems and 7,000 directions, and it's not clear how you would talk about this. So I'm struggling with this right now. In my talk, that was really a new way to look at it, and I'm actually rewriting the talk now. I'm expanding on the talk now for this. So that was my idea about the difference between foundations and philosophy. So, and I go further in the chat and I say, look, the right interaction is when the philosophers finally figure out what should, what does this really mean, and how does it fit historically? How does it fit in historically and in other things that are going on where people use different language in describing what they're doing? The philosophers need to come back to the foundationalists and interact, and then one expects the foundationalists to come up with some additional traction. Now, the philosophers may look at this foundationalist as somebody really not very sophisticated and just sort of operates with a philosophy around the edges, and then get some math going and subjects coming up and being developed and so forth, but they're not really doing philosophy. And then the foundationalist is looking at the philosophers saying, well, they're looking at everything and all these connections, they don't have any traction, right? So they're really two different talents. And I think the idea of having a deeper interaction, and reverse math looks like a good place actually, but there are many other places, seems to be a really good idea that's not been realized. What do you think?
I agree with you completely.
Well, we have this conference now that's getting traction.
Yeah, we're doing that right now.
Did somebody ask me a question?
What about historical facts? Do they have to be correct too, or do we keep going with our?
You mean?
I mean, the Steve's book is full of historical nonsense. If we want to get the philosophy right, do we get the history right too?
We should try to get the history right.
Just for the record, right?
I don't know.
I'm just asking. I mean, no, I'm serious, right? I didn't write the history.
Well, I think the burden is stronger on the philosopher to get the history right than the foundationalist, because the foundationalist can at least leave traction that then then philosophers correct the history surrounding it, and the traction stays there. So I really feel the burden of getting the history really right is more on the philosopher, in my opinion.
Andreas had a question.
And we also have Laura on the chat.
But so but you waited for a long time. So I'll say you go, then Laura, then Damir, and then Andreas.
I can also ask.
Yeah, during the break. Sorry.
Well, great, because I do want to go back to this idea raised earlier about, I guess, it's more of a comment just to defend this point that sometimes mathematics does tell us about something about preserving of kinds. Oh, hi, it's Ainsley asking a question. Steve just asked. So, yeah, because I do think that although it's something that happens a lot, interpreting the right axioms as the natural axioms, that's where I feel most strongly the temptation to call it a confusion and not put it in a kind of positive light. Because I mean, my favorite example is compactness, right? WKL0, like when you get a reversal to that, I feel like a lot of the time it's just telling you that you should have been thinking about this as a form of compactness the whole time. Like that's the essential move, and yeah, it's a way of bringing together all of these theorems as being a kind of compactness, regardless of whether we mean logical compactness or topological compactness. It's just all compactness at the end of the day, and so that's the way that I at least interpret reverse mathematics as being able to give us an example of similarity in kinds, despite going through coding, despite going through interdisciplinary ones. And so if anyone wants to argue with me later about whether or not that is a good example or give more examples on either side, I mean, obviously, that's what us philosophers are here for.
Thank you.
So Laura, then you can speak. You just activate the mic.
Right, can you hear me?
Yes.
Yes. All right, so first of all, thank you very much for this very nice talk. I really enjoyed it very much. I wanted to ask, so I think I have a better grasp of the, say, difference in strength, one of the two ways of understanding. So if you were to try and explain to someone who does not have a full grasp of the other ideas, so you mentioned many different ideas: simplicity, essence. Essence for philosophers, of course, is such a wonderful concept, but so difficult to grasp. So how do we get some sort of feeling of when do we know whether something is within the right kind? So when a proof is faithful to the content, or is the right kind of proof? Is there some general way of saying something about that?
One answer is prejudice, right? That we just learned that this is how things are set up from the beginning, and then we follow up with that. So we might think that geometry and arithmetic are different just because that's how we were trained. But if we were trained differently, we might think that, look, algebraic geometry or analytic geometry is just what really geometry is. And we're going to follow up on that. So that's one answer. For a lot of the time, it's a matter of prejudice. That's not to say that we know anything in that case, but that's how we act. But I was trying to make a case that maybe we have other criteria. Now, just to briefly mention, this guy Frege had this thought that if you looked at the fruitful mathematical pursuits, this would tell you you had the right definitions. But I find that circular, because we only know what's fruitful looking back in retrospect, and that fruitfulness is going to shape our views of what's right or proper. So I was trying to say that reverse mathematics, when we find a reversal, that gives us something more precise that we can pin to and say, here's where we can say what this kind of thing really is. So, I mean, if we want to take the previous example of Königslemma and act this as an example of a reversal, we might say that what compactness then really concerns is walking through trees. This is at least, I went to Notre Dame, so I learned a lot about walking through trees. That was sort of all the courses ended up just being walking through trees. But Peter, they grow up, not down, as he made no shame in telling you again.
Go to the light.
I know. So if you thought that, then that's what you think compactness is really about, is walking through trees. So I think that at least here we've got something that we can rest with some precision that isn't just fruitfulness, and it isn't just prejudice. So consider that a hypothesis about how we could understand this idea of kind or essence in mathematics. And I came up with it because it fits so well with this Aristotelian idea that had already been proposed by Steve. But it's a hypothesis, and maybe it's pretty easy to break. So I'm happy. We'll be looking forward to talking more about that and trying to break it and see how it survives.
Thank you.
Well, thanks. That was a really great talk. Thank you. I'm just curious. So my question's been a little preempted now also by some of you. So I wanted to go back to a couple of these questions, in particular what Alberto was talking about. But I'm curious what you would say. So you take this very broad view of reverse mathematics, and I think it is a very broad, much more broad subject now, but you go even beyond that now. You're sort of saying, you're going to Richard's example, which is a lovely example and kind of, I think, one that we all know, right? This idea that we can communicate somehow with mathematicians who are not reverse mathematicians. And maybe, right, the goal or hope would be that maybe we can tell them something, even if it's maybe not useful to them, but at least interesting, right? Like, there's a reason you're doing it. So, but what would you say that message should really be, right? Because you can imagine that maybe at some point, Ramsey was proving Ramsey's theorem for pairs, and maybe for some reason he didn't come up with the inductive proof, right? He came up with one of these really horrible proofs that we came up with, right? That are terrible proofs from the combinatorial mechanics. They're complicated, they're cumbersome. And he was sitting there, 19 or whatever, thinking about this, really like, gosh, this is using a lot of things that I would not have expected, this is using approximations and this. And then the reverse mathematician comes along and says, I can tell you exactly why. It's because it's, connected to this, and there's this connection of jump of WKL now that's happening. And Frank Ramsey says, that's really interesting, that's telling me something. And then, he goes home the next day and says, no, it's all nonsense. I came up with this really simple inductive proof, right? It's actually, we don't need any of it. So what can, I mean, given that there is this disconnect, right, where sometimes the combinatorial complexity or the kind of combinatorial core, as we would describe it, can be subsumed or replaced by definitional complexity.
Right.
What can be the kind of message of reverse mathematics? You know, at the very least, when we're writing grant applications.
Yeah.
What could we?
I know. It's super important. I think here the lesson is that you've done a good job in identifying this notion of computational content, because then you can single out exactly what it is that you're trying to either optimize or trying to measure. And so you can respond that there may be other things. I mean, gosh, in geometry, there's all kinds of other complexities that are lurking, visual complexity, that aren't necessarily going to show anything about even the combinatorics or the computation, not necessarily. So you can just say, look, this is just one way of measuring exactly what it is that goes into a proof. But we have to admit at the outset there are going to be other ways that may be better responsive if you're a topologist or if you're an algebraic geometer. I mean, there's a reason why logicians, I think, are closer to some parts of mathematics than others. You see a lot of logicians who know a lot of algebraic geometry, know a lot of combinatorics. You don't see so many who work in algebraic topology. That seems to be somehow more distant. Maybe in set theory, you might say there's some more connection there, but it's more distant. Differential equations, I mean, that seems to be also pretty distant. Maybe the people who are working on real analytic model theory, maybe they've got something to do with Mathian things or whatever. But so I think there's a reason why this idea of computational content really does work within the kind of mathematics that we want and that we care about. And some philosophers want to say that really all of mathematics is like that. And I think Walt and I have talked about this kind of thing a lot. Maybe Bernays seem to think that, but I don't. And I think that there's something special to the way we reason geometrically that isn't reducible to computation. So that's where I think the answer can be, just to come back to the question. And so, look, I mean, there's something modest here. I know I want you to give me a lot of money, but recognize that I can't necessarily be responsive to all of the complexities that are going to come out. When Ramsey finds the inductive proof, that's going to answer to different concerns that I'm able to measure with my limited but still successful technique. So I mean, I guess I have to counsel some modesty there, but I think grant agencies appreciate that. But so if you're trying to, I mean, I'm not sure, but at least you don't have to oversell what you do, but you also don't undersell it. You've got a lot of history behind you and a lot of successful mathematics.
So we're a bit late, but
okay.
we have 1 hour to the next talk, so we can go on if you guys want. So Andreas, you have a question.
Yeah, so I wanted to comment on the prime number theorem. So you have this asymptotic bound, which you can obtain by complex analytic methods, by elementary methods. But of course, there's something more to the story, namely the error term. The error term, of course, depends on the methods which you are applying. I think the quality of the error term depends. When you use complex analytic methods, you get very good ones. And when you go more and more elementary, the quality of the error term becomes less good. And of course, the best one you get by Riemann hypothesis, which is even beyond this.
Yes and no. Yeah, right. It's part of the same body of things, but at this point, we don't know. I mean, I should say, I mean, Andreas here is an example of a logician who does know differential equations. So you are maybe the one who's closest to that sort of thing. So you're totally right that this idea of error terms also gets introduced. And I guess I'm not sure that in reverse mathematics, there's a lot of measures of that as opposed to the measure of the strength of the axioms in question. But yeah, when you're looking at convergence results and analysis, yeah, I mean, a question that I've wondered about a lot, and some of you know this, is there some kind of nice real reverse mathematics analysis of Semeretti's theorem? And there, as we know, a lot of the work that's gone into Semeretti's theorem and the other proofs of it involve finding new bounds on the size of it, just like in ring combinatorics regularly, you're looking for bounds on how far you have to look to realize the set you're looking for. And getting that narrower and narrower it turns out to be the thing that wins people fields now. So like Bogan won it for pulling it down, and Bowers also did that. So that's in the same neighborhood, I think, as improving the estimates of error. And as far as I know, reverse mathematics hasn't been able to make much sense of it because these things are doable in too weak a fragment of arithmetic. So I think that people don't really doubt that Semeretti's theorem can be proved, at any rate in RCA not. probably in something weaker. Unlike Ramsey's, it's different than Ramsey's theorem, where surprisingly less structure somehow means you have higher complexity. But Severetti, because there's additive structure, sort of pushes you in and in. But so I guess that's one reason everything you're saying is right. I do wonder if the mathematics has so much structure when we're looking at conditions of, for instance, errors, that maybe the reverse mathematics analysis won't be somehow paradoxically fine-grained enough to tell us it. But I don't know. I mean, that's, I think, so I'm interested if you think something like that too.
Yeah. So there's also a famous result in Ramsey theory when you consider the asymptotics of the Ramsey function. You have the probabilistic method, which is very good bounds, and you have the elementary constructions which don't provide exponential lower bounds. So it's also completely unclear what the situation is. At least as far as I know.
That sounds like an excellent problem for.
Yeah, that's an excellent problem. So come up with an elementary proof of an exponential lower bound, but people tried this for 50 years.
People
in mission impossible.
People in combinatorics, or
yes.
People in logic, or in combinatorics. I mean, that's part of the problem here, is that to really work on this, you need to know that much combinatorics and that much logic.
So Dennis now.
Hi, Andy. So the question is, so thinking about the distinction of these two kinds of issues that you talked about, and thinking of reverse mathematics in the kind of strict sense of like what's covered in Steve's book or what I talk about, as opposed to a more general program, I think it's, well, I don't know, I believe that it's a really good tool for things like minimal axioms and for finding combinatorial chords and so forth. So my question is for the other thing, for this thing, is how good a tool is it actually, right? I mean, it seems to be something that sometimes will really, really work, right? You can show you can't do it using these methods because whatever, but in many cases it won't, because it won't distinguish between areas. So in what sense is reverse mathematics good for that?
The example I would want to point to there is, again, the prime number theorem. So I didn't say much about this, but one of the steps in proving the prime number theorem by complex analysis was an equivalence, a kind of reversal, where Riemann was able to show that the non-existence of zeros of the zeta function on the line with the real part equals 1 is equivalent to the prime number theorem. And then they were able to show the prime number theorem by proving this statement about the zeta function. So it's close to the Riemann hypothesis, but it's not the same thing. So this is a kind of reversal, but I put it in this language kind of, because when you try to put your finger on exactly what the base theory is, or how to state these things formally, you can't do it, and this becomes very topsy-turvy, because there is a proof finally that's given by Selberg and Erdős that avoids, at least some superficial way, the complex analysis. Making sense of that from the point of view of even the reverse mathematics we have now is a task. The way that number theorists understood this, and this is, you can find this in various reviews that appeared right after the Selberg and Erdős proofs, you'll find reviews saying, we were wrong about the logic of number theory, the kind of language that they use. Ingham puts it this way, for instance. And that really, what they say, and even Granville says this in his Princeton encyclopedia or dictionary article, he says that what we've learned is that really tacitly, what looked to be statements about arithmetic were really statements about the complex numbers. That what we think we understand when we understand arithmetic is hiding other things that were lurking there. Now, I don't know what to make of it. As a philosopher, this is tantalizing material, but also very difficult to make sense of. You find this kind of thing being said by number theorists all the time. I remember talking to Ken Ono about number theory. He told me Fermat's last theorem was really about elliptic modular functions, not about number theory itself. And my mind was sort of bent by that. What does that mean, that it's really about that? And I don't know what to make of that. I've always hoped that reverse mathematics could somehow help me with that. But I think, Dennis, your question points out that we're not there yet, and maybe we never will. And maybe part of the problem is that the particular measure that we have at hand, as you said, the combinatorial core or the computational content, just isn't going to be sensitive to that. Maybe something like a different kind of reverse mathematics, maybe something like a strict reverse mathematics, or maybe something that involves some other idea of mathematical content could do it. Because I think the framework of a reversal is really powerful, but the mechanisms involved in that framework are adaptable in the super general way I talked about today. And I'm not sure we've gotten that yet. So I hope that Victor in his talk next will say a little more about how this works in geometry, and that may give us a little bit more to think about here. But even there, the situation is going to be different. So to me, number theory is really a tantalizing case to look at, and I think we just haven't made a lot of progress yet.
Couldn't you just say, like, if you say, well, the truths of arithmetic are somehow only describable in complex analysis, that just means that there's no feasible way of describing arithmetic in arithmetic, which is not such a surprise if you look at good.
Okay, fine, right, so it would be a way of vindicating Turbo, right?
I mean, it's just that the best way of describing or really understanding is probably via complex analysis.
Yeah.
I mean, then so be it.
Yeah, that would make sense. These days I seem to spend more time with model theorists than with computability theorists, and they're all like, yeah, this is why we shouldn't think about the natural numbers at all. Right? This is why arithmetic is bad news. So.
It's like some things are best expressed in some other language than maybe you know. I mean,
yeah.
For those who know other languages.
Yeah, maybe in the end this is the right way to do things, but it's certainly mysterious to make sense of, right? That's sort of our language. I mean, but I guess if you're doing a lot of coding to begin with, maybe you're used to it. You know, you say one thing, but it means another.
Feynman has a nice example in one of his books. Like, there's a guy who's a savant who can do calculations, and they bring him to Feynman, and Feynman sort of gets what the trick is. And Feynman comes up with sort of problems that he knows are very hard to solve with his trick. And so this guy, the first couple, but then when he's up at the fifth, the guy is just, I don't know, what are you coming up with? It was Feynman saw the method and saw, and so this is sort of,
Yeah, so maybe, I mean, you know, I'm saying that math is going to do this someday. That math is going to break out of everything until now has been easy. But there's going to be a new math where somehow self-reference jumps into the picture and they're no longer easy anymore. So, you know, but we haven't gotten there yet. This is his hypothesis that everything that's been proved in number theory until now can be done in EFA. That sort of grander sense. But I guess I find that these things about number theory, they already indicate that. So I guess my hypothesis is. Steve Simpson.
Yes, can everybody hear me? I'm Steve Simpson. Let's see, I have a couple of comments. First is, thank you, Andy, for a wonderful presentation. This is great. You're raising a lot of interesting issues. Second, it made me think of instances in reverse mathematics where two theorems in very different subjects have the same reversal. They're both, let's say, equivalent to WKL0 over RCA0. An example is, you know, theorems about continuous functions on the unit interval are equivalent to the theorem that every, let's say, countable ring has a prime ideal. This is ridiculous from a mathematical point of view. These theorems are not equivalent. It depends what you mean by equivalence. So is there some way to formalize what we mean? In other words, the first idea that comes to my mind is these are in different fields, and there should be maybe for us, you know, for you philosophers. I'm an amateur philosopher, although I'm a big fan of Aristotle. Maybe there's some way for us to analyze this situation and have foundations of different fields of mathematics, such as foundations of algebra versus foundations of analysis. So that's about what I have to say. Has there been any serious attempt to do anything like this? Oh, one more thing about the prime number theorem. What I think is true what I think is going to result here is that you can probably do all that complex analysis in appropriate definitional extensions of WKL0 or something like that, or maybe RCA0, and then you can just prove it. That a consequence would be that the prime number theorem is provable in primitive recursive arithmetic. Of course, that doesn't say that it's provable by elementary number theory means, because primitive recursive arithmetic includes all kinds of stuff. But maybe you could even do it in WKL0 star, which only has elementary functions. So that's what I think is going to be the outcome here. But an outcome. But I'd like to see something more clearer on that.
Yeah,
I think the prime number theorem, it's already been done.
Okay,
in
that's about all I have to say.
Yeah, thank you, Steve. So just to answer your question there on the prime number theorem, yeah, so it can be done. The complex analysis proofs, the Takeuchi was able to formalize it in a conservative extension of PA. And then a student here in Paris named Sudak was able to show finally that it could be done in I sigma 1. So that proof, the classical complex proof is doable in I sigma 1. I think that's best now. The Selberg proof was formalized by these two people I mentioned, Karnaros and Dimitriokopoulos, in PRA. So we do have those two proofs formalized and pushed down pretty far. And maybe those results can be improved, but we do know some things about them. That's, in a sense, my comment about the complex analysis then was to say, is there a way to make sense of what seems to number theorists to be a difference between the mysterious methods of analytic continuation, which you need to define the zeta function, at least for the whole complex line, whole complex plane, and the non-deep methods. Is there some way to make that distinction salient in a context that we have our hands on in reverse mathematics? And until now, I don't know. I was disappointed when I saw all these things could be done in such weak theories, because then what the number theorists are seeing just dissolves in this setting.
The big elephant in the room is FLT, you know.
Well, I want to see it, yeah.
Follow McClarty. McClarty is the one who's sort of most published on this, and is only claiming to bring it down to nth order arithmetic, where he won't quite say what n is. And the original proof used Grothendieck, referred to Grothendieck universes. So the original proof actually is not even in ZFC.
Right. But now McIntyre even claimed, I think, that it can be done in PA. And
yeah, he claimed that, but he also claimed that he had no way of justifying that because there's there's too much material that has to be done. I say that probably provable in EFA.
Yeah, I think number theorists mostly agree with that. But then again, it just shows us that these methods are not registering the mathematical complexity. But I wanted to come back to Steve's question. I'm sorry, I'm taking advantage of all of you sitting here. We can all go and get coffee. Steve did ask 3 questions or 3 comments, and the second one was about looking at any way to make formal these distinctions between domains of mathematics. So a long time ago at a lunch, Dennis Hirschfeld suggested to me to use methods from Kolmogorov complexity, in particular involving the so-called information measures, to try to do this. And I had a master's student look at it a long time ago, and he wasn't able to do anything with this. But there might be some hope to try to implement a way of distinguishing, even just syntactically, the differences between different mathematical areas. In the case of reverse mathematics, your point was extremely well taken. What does the existence and uniqueness of solutions to ordinary differential equations have to do with the existence of a prime ideal, existence and uniqueness, for instance, or a maximal ideal? You know, these don't look like they have anything in common. So whatever reverse mathematics is showing us in terms of these equivalences, it's blending areas together. And again, I think there's a response to be made, which is that, well, computationally, these blur together. But there's more to meaning in mathematics than computation. But then that's just to defer your question to another time and to say, I guess I just don't know at this point how to do it. Aside from this potential loose end, maybe even more than that, hope of measuring syntactically the difference between the domains of mathematics. You know, maybe it's just that when you say something geometrically, it ends up looking different syntactically than when you say something arithmetically. But that's just, at this point, super vague. So I have to beg in ignorance there. I think it's a fantastic question. Even though we like to talk about mathematics as being a unity, we all know that it also maintains a certain disunity at the same time. And we still, when the AMS divides mathematics into all of these different areas, that's supposed to mean something. We all know that the NSF has different sections for what we apply to for our grants, and so on. So, and we teach courses that have names like differential equations, algebraic geometry. We think that those are different courses. So some way of justifying that that isn't just mere prejudice would be a great thing to do. I've been working on that for a while, and hopefully someday we'll be able to do something even precise about that. And I'd like to say that reverse mathematics maybe can be part of the story, but it probably won't be just reverse mathematics in terms of computational content, because that just blurs too many things that are salient.
Steve, if you have a really quick follow-up, you can go, but then we're going to stop because we have to stop at some point.
Give me a second.
Yeah.
No, apparently it was a long follow-up.
No, okay. So we're going to stop.
No,
okay, go.
Please, yeah. Yeah, we can hear you, Steve.
I raised my hand before, but now I think Andy has answered my question. In other words, not much is known about this idea of foundations of different fields. Certainly not anything that's been formalized. So that you know, but it's very thought provoking, and this is a great talk, Andy. Thank you.
There's a question in the Q&A thing. I can read it if you want. And the question is there any way to say what natural even means? Perhaps the other notions are an attempt to explicate natural.
Yeah, that sounds reasonable. I mean, natural is a sociological thing, I think. But I mean, even sociology maybe admits some logic, but we're just not there yet. I think that's really the best that I can say.
Okay, so let's thank Andy again.